Okay, so welcome. So, can you hear me? Hello.
Yes.
Okay,
Uh,
and is the note visible?
yes, it is.
Okay, okay. So, well, people are still joining. So, welcome to the first session of the tutorial of this quantum mechanics course. So, this is the quantum mechanics 1. So, we will learn about the basics of how to use the Dirac bracket notation and all that. That is quite powerful mechanism, and I mean it is advantageous to use this mechanism over the usual wave function method. So in later lectures, the power of this mechanism will be manifest. So today we'll just recapitulate our old knowledge about these wave function methods and review some common systems like particle in a box, then simple harmonic oscillator, then delta function potential, potential barriers, etc. So the first assignment is due on I think 8th of February. So and I'll be discussing about two assignments, like similar questions that you will need to solve in these two assignments. So please remember that the first two assignments are due on this week. So assignment 1 and 2. So let us start. So I hope that you all remember how to calculate the expectation values in wave function method. So this was one of the prerequisites for the course. So let us start with a simple Compton scattering problem. Okay, so this looks like one of the problem. So consider a photon scattering from an electron at rest. Okay, now the photon scatters at an angle 60 degree with a wavelength lambda dash. The final wavelength is lambda dash and the initial wavelength is lambda, and we are given that lambda dash is twice that of the initial wavelength lambda. So we have to find the angle at which the electron recoils, and also we have to find the incident wavelength lambda. Okay, so this is the Compton scattering scenario. So consider this diagram. So in this diagram, so gamma is, I mean, we denote a photon by this gamma, and E minus is electron, and these phi and theta angles are the angles of recoil. So as you can see in this diagram, so gamma, so the angle of scattering of the photon, so this is photon, so denoted by gamma. So angle of scattering of the photon is denoted by phi. Okay, so this is the angle between the initial direction of the photon and the final direction of the photon. So this is the scattering angle of the photon, which is phi. and the recoil angle of electron is theta. So this is the angle between the initial direction of the photon and the final direction of the electron. So these two are the angles, and PF is the final momentum of photon, PI is the initial momentum of photon, and PE is the final momentum of electron. And electron was at rest at first, so there is no momentum of the electron to begin with. So now, as you know, so we'll now have to use various conservation laws, namely the conservation laws of energy and momentum. So let's begin. So the momentum conservation. So this is the momentum conservation equation. So initial total momentum was Pi and the final is Pf plus Pe. This is vector summation. And of course from simple vector algebra, this relation implies this one. So I have just taken vector dot product to arrive at this result. Okay. Well, so now we have found a relation between the momentum of various particles, and now okay, and now we will be using concepts from quantum mechanics. So as we know, so the relation between a photon's momentum, so relation between a photon's momentum and its wavelength, so which is the t Broglie wavelength, is given by this relation. Is given by this relation. So magnitude of a photon's momentum is equal to h by lambda, where lambda is the wavelength of the photon. Okay, so we will have to use this relation. And now also, so we have written this momentum conservation relation like this, and then we will resolve this relation into components. So as you expect, so two components, I mean the resolution into two components is sufficient. So one resolution is needed along the initial direction of photon's momentum, and the second resolution is needed so along the perpendicular direction to the initial momentum direction. So along the direction of the photon's initial momentum, so if we equate those components, so we will get this relation. So simple. So Pi was the initial momentum in that direction, and P cos theta and Pf cos phi are the components, so components of the final momentum along that direction. So of course, so in that direction the momentum need to be constant, so that leads to this relation, and then in the perpendicular direction we get this one. So it's very easy to understand. Just resolution into components of a vector. So thus we have got these two relations by resolving the momentum conservation equation into individual components. So now, so in question we are asked to find the recoil angle of the electron. So from our earlier discussion we know that, so we have to find the theta, and in question the scattering angle of the photon was given. So the scattering angle of photon, which is phi, this was given in the question as 60 degree. So photon scatters at 60 degree. So phi is given at 60 degree, and given this we have to find the angle at which the electron recoils. That means we have to find theta. So given phi equal to 60 degree, we have to find theta. So we'll see that these two relations will be sufficient for that. So now what I have done, so consider these steps. This tan theta, of course you know tan theta means sine theta by cos theta, and then I have simply multiplied by p in numerator and denominator, and then I have used the momentum conservation relations. So you know p sine theta is pf sine phi, and p cos theta is pi minus pf cos phi. Okay, so up to this much is fine. And now, so pi and pf are the initial and final momentum of the photon, and that means this can be expressed in terms of the initial and final wavelength of the photon, since we know the de Broglie relationship between the wavelength and momentum of the photon. So using the de Broglie relationship, we get this one. So lambda dash is final momentum and lambda is initial momentum of the photon. Now we will use various values of the parameters given in the question. Right? So we are given in question that lambda dash equal to 2 lambda and phi is 60 degree. Now just simply substitute here and put sine 60 degree, cos 60 degree, etc. And then you will get tan theta is 1 by root 3. That means theta is 30 degree. So the final answer is the recoil angle of electron is 30 degree. So, okay, we just needed to use the momentum conservation law to find this recoil angle. Now, we will need to find the value of the incident wavelength lambda. Okay, so for this we need to use the original Compton scattering relation. So okay, here I have presented a derivation, but I think that in the lecture okay, so I think that you are all familiar with this formula, right? So please someone respond. Okay. Okay. Well, so if you are not familiar, then I will go through the derivation. So like as we have just seen, so to find the recoil angle, we have just used the momentum conservation law, but there is another one. So the energy conservation law can also be used. So let us now use that. So this is the energy conservation law. So EI gamma. So EI gamma is the initial energy of the photon. So total initial energy is equal to total final energy. So this is the energy conservation law. So what quantities contribute to the initial energy? So this is the photon energy and electrons rest mass energy. Remember, so in relativity, you know the relation E is equal to mc square, where m is, so for a particle in a rest, m is the rest mass. Okay, so for a particle in a rest, so E is equal to mc square. So for a particle in a rest, m is the rest mass of that particle. So our initial electron was at rest, so the rest mass energy should be considered. And in the right hand side, what contributes to the final energy. So this is the, so these are the final energy of the photon and the final energy of the electron. Now remember, now the final electron is moving, so there will be rest mass energy and some other contribution. So let us consider this component. So the electron energy, so so electron energy is E is equal to Cp. So P is the magnitude of the momentum vector of the photon. So this is the relativistic relation, and of course this is equal to hc by lambda due to this de Broglie relation. Okay, so so E is equal to hc by lambda. So this will be useful for our case, since we are given a relation between lambda initial and lambda final. Okay, so E gamma is this. So as I said earlier, so E raised, so the initial energy of the electron is mec square. So me is the electron mass, and now the final electron energy. So the final electron energy is this. So me square c to the power 4 plus c square p square. So this is the relativistic relation. So I think you are all familiar with this one. So this is the relativistic energy of massive particles. So now simply put these values in the energy conservation equation and you will get this. And now there is some algebra. So like bringing some terms from left hand side to right hand side to make it into a less cumbersome form, and then take the square, use this vector algebra. So this one. So now there is no physics, just some vector algebra. And then, okay, so after reaching this step, so all we need to do is to use this de Broglie relationship for photon. So Pi and Pf, so Pi means h by lambda and Pf means h by lambda dash. Similarly in the right hand side, okay, similarly in the right hand side, and okay, put this P is equal to h by lambda relation, and you will get this Compton scattering formula. So you just have to do it yourself once and you will simply get hold of this algebra. So there is nothing much. So physics wise there is nothing much. So you have to just use this momentum conservation relation and energy conservation relation, and this de Broglie momentum wavelength relation, and then the relativistic energy momentum relation. So these four things should be used, and then after doing algebra you will get this Compton scattering formula. So this formula gives the difference between the wavelength of the scattered photon. So lambda dash is final wavelength and lambda is initial wavelength of the photon. So me is the electron mass, and cos phi, so what was phi? Phi was the scattering angle of the photon. So the Compton formula gives a relation between change in wavelength of the scattered photon and the angle of scattering of the photon. So now we are given lambda dash is equal to 2 lambda, and cos phi was given as, and phi was given as 60 degree. Put that, so lambda dash minus lambda will be lambda because lambda dash is 2 lambda, and cos phi for phi 60 degrees half. So substitute these values that are given in question, and you will get lambda is equal to h by 2 MEC. Substitute the values for h, me, and c, so that are readily available anywhere on the internet, and you will get initial lambda to be this one. So 0.13 into 10 to the power minus 11 meter. So this answers the question. Okay, so we have just completed our first question. So if there is any question, please feel free to ask. Okay, if not, then I'll move on to the second question. And now this involves solving for energy eigenvalues and all these things. So we'll consider the simplest case of all. So that is the particle in a box. So I hope you are all familiar with this particle in 1D box and its higher dimensional generalizations like particle in square box, particle in 3D cubic box, etc. So in this question, so we'll consider a particle in a square box. So the potential inside the square box is 0 and outside the square box is infinite. So it is an infinite square well. So 2D generalization of the particle in a potential well. So this is the problem statement. So consider a particle in a square box 2D whose ground state energy is epsilon naught. So the question is E is equal to 25 epsilon naught an allowed energy level? So as we all know, in what happens in 1D infinite potential well, so if epsilon naught is the ground state, then the second energy level is 4 epsilon naught, then 9 epsilon naught. But in between, like 2 epsilon naught or 7 epsilon naught, these are not allowed energy levels, right? So the energy levels varies as n square. So not uh, all integral multiples of epsilon naught is a allowed energy level. So only the energy levels that varies as n square is an allowed energy level. So similarly in this case we will see that not all integral multiples of epsilon naught is an allowed energy level. So that is why the question. So is 25 epsilon naught an allowed energy level? Okay. So how do we find that? So of course, as we know, the energy level in a 2D square box will be this one. Okay, this one. So now the energy levels will be characterized by two positive integers n and m. In 1D case we needed only one integer n, so we consider positive integers. So here we need two integers n and m. So suppose n is for x-axis and m is for y-axis. So the energy levels are this one. So n square. So of course you know this factor h square by 8ma square. So a is the side of the square box. So the energy levels are n square h square divided by 8ma square plus m square h square divided by 8ma square. Okay, so a notational problem. So I am mistakenly denoting both mass and an energy level m as m. I hope you can distinguish between these two. If not, please ask. So the m downstairs is mass and the m upstairs is the integer that denote an energy level. Okay. So now what will happen to the ground state energy? So so since n and m are positive integers, so the least values they can take is 1 comma 1. So the ground state energy will be obtained if we substitute 1 for both n and m. Okay, we do that and we get this. So the ground state energy is EGS, that is denoted at epsilon naught in question, and this is equal to E1 comma 1 that we have just discussed. Simply substitute 1 comma 1 in this relation and you will get this as the ground state energy. So put n equal to 1 and m equal to 1 and you will get 2, and this is the ground state energy. So our ground state energy is epsilon naught is equal to 2h square divided by 8m square. Okay. So now we will express all the energy levels in terms of epsilon naught instead of this h square by 8m square factor. Okay. Now see, h square by 8m square is equal to epsilon naught by 2. So that is why we have got this relation. ENM is n square plus m square by 2 multiplied by epsilon naught. Okay. So this is the relation between the ground state energy and energy of an allowed energy level. Now, as you can understand, the question simplifies into this question. So, does n square by n square plus m square divided by 2 is equal to 25? Does this equation has positive integer solutions? So if we can get solution for this equation, so then this 25 epsilon naught energy level will be allowed. If this equation has no integer solution, then will not then that energy level will not be allowed. So there is no straightforward algorithm, but you can rely on your observation. So you see that yes, there are solutions. These solutions are 1,7. Of course, then 7,1 will be another, and then 5,5. So there are 3 solutions to this equation. N square plus m square by 2 is equal to 25. So since we are getting at least one solution, so that means this E is equal to 25 epsilon naught is an allowed energy level. Okay. And moreover, we are getting 3 solutions, right? So n comma n has 3 defined values. So that means this allowed energy level has 3-fold degeneracy. So not only this 25 epsilon naught an allowed energy level, but it has a 3-fold degeneracy. So okay, so that solves our second problem. So that is how you have to solve these problems. So next we will consider a similar problem but in 3D case. So before that, if you have any question, please ask. Yes, that is correct. But you see, so yeah, I'm talking regarding this question. So what you have written is correct, but you see, I am using h, right? So you were talking about h cut square. So I am using h. So if you just substitute h cut equal to h by 2 pi in your relation, then you will get this h square by 8m square factor. So simple thing. what you have written is also valid, but yeah, just substitute h is equal to 2 pi h cut. Yes, nothing changes. Okay, so I guess no more questions. So similar problem now, but in 3D. So find the sixth energy level of a particle in a cubical box in terms of the ground state energy epsilon naught. So same kind of problem, but sixth energy level. So we will see that this is a bit non-trivial. So what would have happened had we had a particle in one-dimensional box? So 6 energy level would simply be 36 multiplied by ground state energy, right? So 36 epsilon naught would have been the answer, but you will see here that here the answer will be not that high, but much more less than that. So of course we generalize the 1D result for the energy levels and get this as 3D result. So the energy level, so in 3D we'll need three integers to characterize the energy levels. So we call them L, M and N. Okay. And the energy levels are E, L, M, N is equal to L square plus M square plus N square multiplied by A square by 8M square, where L, M, N are all positive integers. Okay, so simple. You can think L to be X direction, M to be Y, and N to be Z direction. So three integers to characterize three directions. So you can simply think like that. So the energy levels is given by this. Okay. So of course you know, since L, M, N are positive integers, so when do we get the ground state? So we get the ground state when we consider L, M, N all to be equal to 1. Okay, so if we substitute 1 in the above relation, we'll get this relation. So EGS, so that is given to be epsilon naught in question, and we just discussed that the ground state energy will be obtained if we substitute LMN to be 1, 1 and 1, and simply substitute 1, 1, 1 in this above relation, and you will get 3 multiplied by h square plus 8m square. So now we get the relation between this factor and the ground state energy. So this is the relation. Good. So since we now have this relation, okay, since we now have this relation, that means we can write it like that. So ELMN is equal to this L square plus M square plus N square divided by 3 multiplied by epsilon. So now this is the relation of the higher energy levels and the energy of the ground state. So now we need to find the energies, and there is no straightforward way to do that, because a element can take an integer values, and I want to say that this is not very straightforward like the 1D case where you just needed to put n square and get the answer. Here we have to I mean, do this by trial and error method. So substitute various values of L, M, N and see which is the sixth lowest energy level. So like here I have prepared a table up to the sixth energy level and see what happens. So as we saw, LMN is 111. So this was the ground state, epsilon naught, and its degeneracy is 1 because no other values of LMN can give us this epsilon naught energy eigenvalue. Now of course you can anticipate that when we'll use 112 or 121 or 2111, sorry, or 211, then you will get the second energy level, that means the first excited state. Substitute that, so substitute 112 here and you will get 2. So 1 plus 1 2 and 2 square is 4, that means 6 by 3 is 2. Okay, so substituting 1 1 2 in that relation, you will get the energy eigenvalue is 2 epsilon naught and degeneracy is 3, because here I have just written 1 1 2, like L takes 1, M takes 1 and N takes 2. Yes, so as someone is asking, what if we use 222, and you will see that 222 is of course an allowed energy eigenvalue, but its energy eigenvalue will be higher. So it is not the first excited state, so it will be a higher excited state. In fact, you will see that in this table. So you see this 222 is here. So it has the energy eigenvalue of 4 epsilon naught, and you can see from the table that it is the fifth lowest energy eigenvalue. So that means it is fourth excited state. Okay, and the second excited state is only this. Then similarly, the third one is this 122, and this has a value of 3 epsilon naught. Okay, degeneracy. So wasn't degeneracy covered in lecture? Not sure. So degeneracy means like here you see, so your energy levels are characterized by 3 integers like L, M and N. Okay, so now as you can see, so there may be cases when different combination of L, M and N can lead to a same value of L square plus M square plus N square. So when that is the case, so we call the energy to be degenerate, right? So let us look at this case. So you see here I have written L M N as 112, right? So 112 means 1 square plus 2 square plus 3 square, sorry, 1 square plus 1 square plus 2 square gives us 6. So 6 by 3 2. So since additions are what they call it, associative, okay, associative and commutative, so that means instead of this 112 we could have used 121 also. So had we used 121 instead of 112, we would have obtained 2 epsilon naught again, because 1 square plus 2 square plus 1 square is again 6, and divide that by 3 and you will get 2. And then instead of 112 and 121 we could have also used 211, and of course as it is evident by now, that would also lead to the energy level 2 epsilon naught. So you see, so we get the energy level 2 epsilon naught by considering three different combinations of L, M and N. So one is 1, 1, 2, another is 1, 2, 1, and the another is 2, 1, 1. So three different combinations. So these L, M and N are ordered collections. So 112 is defined from 121 and that is defined from 211. So three different combination lead us to the same energy eigenvalue 2 epsilon naught, and that is why we call it we call the degeneracy of this energy level 3, because you have three different states that has the same energy eigenvalue. So that is the meaning of the degeneracy. So I hope it's clear a little bit. Okay. So now let us move on. So the third one is 122, and you see this is again degeneracy 3, because instead of 122 we could have considered 212 or 221. So all of them will give you energy eigenvalue as 3 epsilon naught. So that is why the degeneracy is 3. So then the fourth one. So the fourth one is 113. So 113 gives you 11 by 3 epsilon naught. Again degeneracy 3. Now someone was asking what about 222? So this is here. So you see this is the fifth energy eigenvalue. This is the fourth excited state. So this is the eigenvalue is 4 epsilon naught, and its degeneracy is 1. 1 because only the 2 comma 2 comma 2 can give us this 4 epsilon naught energy level. Now the next one will be the sixth one that we need, and we get that by substituting 1 comma 2 comma 3, and that is 14 by 3 epsilon naught. That is 14 by 3 epsilon naught, and its degeneracy is 6. Like we have defined values for L, M and N, and we can take all the permutations. So three defined values can be permutated in 3 factorial, meaning 6 defined ways. So that is why the degeneracy is 6. So like I have written just 1, 2, 3. You could have written also 1, 3, 2, and then 2, 1, 3, and then 2, 3, 1, and then 3, 1, 2, and 3, 2, 1. So these are the 6 uh, ordered collection of L, M and N, and all of them would have given you this 14 by 3 epsilon naught eigenvalue. And since these 6 states give you the same energy eigenvalue, so that is why this energy eigenlevel has degeneracy 6. So that is the answer. So we needed to find the sixth energy level, and our answer is this. So the sixth energy level is 14 by 3 epsilon naught, its degeneracy is 6, and so on. Okay, so here I have looked at the assignment question and think that there is some mistake in the question. So in the question, well, in the question you needed to find the degeneracy of the energy level 6 epsilon naught. Well, let me check. Well, okay, anyway. So, yes, in the question they have written that 6 epsilon naught is the second energy level. Okay, but here I have just shown you that the second energy level is 2 epsilon naught. But they have written 6 epsilon naught as the second energy level. So I guess they have somehow not considered this 1 by 3 factor here. So the question is this. So the 6 epsilon naught is the second energy eigenlevel. Okay, and you have to find the degeneracy of the next energy level. So degeneracy of the next energy level, that means according to them you have to find the degeneracy of the third energy level. Here it is 3, but I guess if you consider the correct order, like 6 epsilon naught is actually the 8th energy eigenlevel, and that has 3-fold degeneracy. And I have checked that the ninth energy eigenlevel will also have 3-fold degeneracy. So you can simply write 3 as the answer. uh, Degeneracy is not energy level but of degeneracy of a energy level. So energy level are these values, right? So these values are the energy levels, and degeneracy is an integer like 1 2 3 kind of. So an energy level are these. So as I have explained, so in how many ways can you mm, like here, so here you need three integers L, M, and N to represent an energy level, right? So the degeneracy is in how many different ways you can represent a particular energy level, like this one. How many ways, in how many ways you can represent these 3 epsilon naught energy level. Okay, so as I have explained, so you can do this in 3 ways. Like one is 122, which I have written. Another one will be 212, and the last one will be 221. So three representations, and all of them have same energy eigenvalue 3 epsilon naught. So since 3 epsilon naught energy eigenlevel can be reached in 3 different ways, like in 3 different representation of L, M, and N, so that is why the degeneracy is 3. So that is the concept of degeneracy. Okay. So is it not 110? So you see, so if you take n and m to be 0, so the wave function will be automatically 0. Okay, so that is why we take the 1 1 1. So 1 0 0 will mm, I mean will not represent a particle in a box, because then the wave function is automatically 0 everywhere. As you see, in particle in one dimensional box, so the energy level starts from 1, right? So this is, the wave function is sine n pi x by a. So if you, so here we simply have, so in the case of cubic box or square box, we will simply have sine n pi x by a multiplied by sine n pi y by a multiplied by sine n pi z by a. Sorry. Okay, so sine n pi x by a, sine m pi y by a, and sine l pi z by a. So you see, if you put any one of n, m or l to be 0, so your wave function immediately terminates to 0. That means that wave function does not represent any particle, because you know, using 0 wave function you will get probability density 0 everywhere. So that is why you cannot use n, m and l to be 0. So they have to take positive integer values. Okay, so this is the problem. And now we move on to something different. Like, okay, this one is the easy one. Like, you are given a wave function. Like, I hope you are familiar with the normalization. Like, a wave function is given and you will have to find the normalization constant. So the wave function for a particle at a particular time is given by this. So this is the wave function at time t equal to 0. So this is a piecewise continuous function. So up to 0 to a, this is x by a. Up to a to b, this is b minus x divided by b minus a. And elsewhere it is 0. So this is a piecewise continuous function. And you may check that at x equal to a, this function is continuous but not differentiable.
Hello, sir.
Okay, yes.
Sir, what is the meaning of piecewise continuous function? What is the sense
Okay,
when we say the piecewise continuous functions? Like,
yes, yes. So that is not really important here, but anyway. So you see, if you plot the
I always hear in quantum mechanics topic piecewise continuous. Like,
okay, okay. So if you plot the graph actually, so you will see that x by a will be a straight line, and b minus x divided by b minus a, this will also be a straight line, right? But these are two different straight lines, and well, these are two defined straight lines and intersecting. So this is not really one continuous function. How to put it?
and we can imagine it is a lots of piece which is continuous in a small interval like this.
Yes, yes. In essence, that is the case, because you see, so x by
Yes, I am looking the wave function. Yes.
yes, yes, x by a is continuous up to this interval, and the second one, this is also continuous in the given interval. So
Okay.
kind of okay. The
And if it is not piecewise, then it is not normalizable and so on. Like,
I
is it?
mean, you have to. So what are the properties of a function? So it has to be continuous and single value, right?
Yes.
Yes, the continuity is important. So here you see, so
Yes.
you may think that at x equal to a, the continuity may break down, but put x equal to a, so what will you get? So at x equal to a, this is a, and at x equal to a, this is also a. So at x equal to a, this function is continuous. Similarly, at x equal to b, both are 0.
Yes.
Yes, so the wave function is continuous but not differentiable. But the differentiability criteria is not very much needed. Yes,
Yes.
yes. So now,
Okay.
given this wave function, we have to find the normalization constant A. So of course it's a easy problem. So what to do? So the probability density, its integral over all space is 1. So probability density means modulus of psi, its square. This is the probability density, and its integral over the all interval is 1. So just do this, substitute this piecewise continuous function like up to 0 to a. You need to substitute this because that is what is the value of psi x in this interval, and from a to b substitute this, and elsewhere it's 0, and that is why I have not write that 0 contributions, and then perform this simple integrals, and this gives you this result. And normalizable means this and normalizable means this is needed to be set to equal to 1, and that means mod a square is 3 by b. That is what we need, and then a is equal to root 3 by b is a valid choice. So I have written it choice because you could have multiplied it with arbitrary phase factor e to the power i5, and nothing would have changed. But we do not do so, and we simply keep the normalization constant real. So this is a valid choice. So that was an easy problem. Okay. Now the next one. Okay. The wave function for a free particle of mass m is given. So this is the wave function psi x comma t e to the power I kx minus et by h cut. So this is the wave function for a particle of mass m. Now we have to find the uncertainty in its momentum and the probability current density. So let us first look at the uncertainty in momentum. So what is the definition of uncertainty? So this one. So uncertainty in momentum delta.
Sir,
Yes.
can we not use Fourier transformation for the free particle?
Yes, we can.
So, sir, why you have using different notation? For example, you have taken expectation value of momentum space, right?
Momentum operator. Yes.
Yes, sir. So I was because in previous lecture, ma'am, in the lecture video, they told us to use Fourier transformation for the free particle because it is because free particles considering scattering state.
Yes.
So they tell us that use Fourier transformation for that. So I was asking that we can use that also.
Yes, you can use that also in Fourier space. The analysis is easy. So,
Yes, sir. Thank you, sir.
Okay, so what will happen in the Fourier space? So what will be the Fourier space wave function? So can you tell?
1 minute, sir.
Yes.
It will
Yes.
be 1 by root 2 pi h cut integration of minus infinity to infinity psi of x e raised to I kx minus et by h bar.
Yes, but you need to actually evaluate that integral, right?
Yes, sir.
Yes.
It is easy, I think.
Yes, that is easy. So that will give you a delta function.
Delta function, yes, sir.
So the Fourier space wave function is delta function of p minus kh cut.
Yes, sir.
Delta p minus kh cut, and then you know how the momentum operator acts on the momentum space wave function.
Are you talking about partiality theorem, sir?
What theorem?
Partiality theorem. Parseval, sorry, Parseval theorem.
No, Parseval's identity. No, I'm not talking about that. So I mean, like,
I'm
in position space, so how do x act? So x means,
yes, sir. Yes, sir.
yes,
Yes, sir.
you simply multiply by x, right?
Yes, sir.
Yes.
Okay.
In the momentum space, the momentum operator acts similarly. Like you simply
Oh,
multiply by p.
okay, okay, okay. I
Yes.
got that. Thank you, sir.
You simply multiply by p, and then if you use that momentum space delta function and repeat the analysis, you will get this answer kh cut.
KH. Okay,
Okay.
sir.
Yes, that is another way to do it. But in most of the cases, in most of the cases, we use simply the position space wave function. So that is why I have chosen to use it here also.
Oh, okay, sir.
Okay?
Thank you.
Yes. Yeah, that was quite useful discussion. Yes. So in position space, P acts like IH ka del x. This is the position space representation of the momentum operator. Now use this and do the algebra and you will get kh cut, and similarly for p square, so p square operator, so consider the square of this operator IH cut del x square, so this is nothing but minus h cut square multiplied by this del to del x2 thing. Now just
Sir,
differentiate. Yes.
one question. In the equation of P operator, you have
Yes.
divided by integration of dx into psi star into psi.
Yes.
For normalization, or is that another thing?
No, it's for normalization.
Oh,
Yes. Because, okay, here you actually run into a problem because strictly speaking, the free particle wave function is not normalizable, right?
yes, sir. That's
Yes,
why I was asking.
that is why. So, otherwise, there is a problem, and now since you are getting this kind of form, you
Yes,
will
sir.
just cancel the numerator and denominator.
You know.
Yes, that is why. And similarly, well, okay. And similarly for p square also, same thing. And you will get this k square h cut square. So what do we have? We have the expectation value of p square to be k square h cut square, and we also have the square of the expectation value of p to be k square h cut square. So both of them are same, and that means if we substitute that in this relation, we will get delta p to be 0. So delta p is 0. So this means that this free particle wave function as written here is a momentum eigenstate. So in these states we have a definite value of momentum. So that is why the uncertainty in momentum is 0, because momentum is definite. So can you now say, so what will be the uncertainty in x for these states?
I think 0, sir.
Uh, why 0? Uh, you have this Heisenberg uncertainty relation. So
Yes.
delta x delta p is greater than equal to,
greater than equal to h cut upon 2.
yes, and you have delta p is 0. So then delta x has to be
0.
no non-zero. So 0 multiplied by 0 is 0. So then Heisenberg uncertainty is violated.
Okay, sir.
Okay, so
So it is infinite.
yes, delta x has to be infinite. So this is the statement. So here, okay, so here delta. So you have definite momentum, and since you definitely know the momentum, that means you know nothing about the position. So that is the essence of the Heisenberg inequality. Sorry, uncertainty. Yeah. Since you definitely know the momentum here, and that is why this uncertainty in momentum is 0, that is why the uncertainty's position is infinite. Now the probability current density. So do you know about the probability current density?
Yes, sir, little bit.
Yes, sir. Mode of
Yes. Okay.
it is mode of psi xt square.
That is probability density. So I am asking about probability current density. Those are two different things.
Sir, is it minus h cut by 2 mi psi star into dou psi of ds
Yes.
plus
That thing,
psi?
that thing.
Okay, that
Yes,
one.
yes. So then I will not go through the derivation.
Yes, sir,
So
you can skip the derivation.
yes. This is the thing. Yes. So this is the thing. Probability current density, and this is the probability density. So you know the nomenclature follows from this continuity relation in classical electrodynamics or say classical fluid dynamics. So this is the
Yes, sir.
continuity relation.
Classical conservation of electrodynamics.
Yes. And this is also for fluid dynamics also. Charge density and current density. This is the relation, and we try to get the Schrodinger equation in this form, and from there del rho is like, so rho is like charge density and J is like current density, and this is this thing. So now since you know about this probability current density, all you need to do is to substitute the given wave function, and you will get this. So and curiously there is one thing for free particle. So this is the relation B, this is the probability current density, and the probability density for free particle is mod A square. So that means there is a relation between, I mean, direct relation between the rho and J for a free particle. Okay, rho and J for free particle, and that is well, well, this is the relation. Okay, so J is equal to h cut k divided by m multiplied by rho. And do you recognize what is h cut k by m for a free particle? So
Momentum.
no, h cut k is momentum, and
Kinetic energy.
no, h cut k by m. So if h cut k is momentum, then what is momentum by m? So this is like velocity or speed. So h cut k is momentum, so divide that by m, so that is like speed. So then for free particle we get the equation J is equal to rho v. So I think this relation is also familiar. So the relation between charge density and current density, J is equal to rho V. Well, this straightforward interpretation is for free particle only, okay? That is not valid for, say, simple harmonic oscillator. Okay. Now next question. What is it? Well, so again 1D infinite well. So now we'll be talking about 1D infinite well. So the walls are at x equal to 0 and x equal to a. Now we have to find the expectation value of position in the nth energy level. So easy problem. So you know the nth energy level wave function is this one, root 2 by a sine n by x by a, where n is a positive integer. This is the normalized wave function. And now simply, how do you find the expectation value of position? So this is the integral. So these are already normalized, so there is nothing in the denominator. So this is how you find the expectation value of position. Now you have to simply perform the integration. And after performing the integral, you will get a by 2. So the result is at the middle of the well. So the expectation value is a by 2. That means at the middle of the well, and more importantly, it is independent of n. So for any n, the expectation value is a by 2. Okay, so there is nothing more to discuss about this problem. Now an important problem. So delta function potential. So are you familiar with the delta function potential?
Dirac delta or simply delta?
Yes, Dirac delta.
Yes, sir.
Okay. So you know how to derive this energy state, like? So
Yes, sir.
okay. Well then,
Actually, sir, please explain Dirac delta potential.
okay, yes, I'll do that quickly. Okay. So the particle of mass m is subjected to an attractive delta function potential. So the adjective attractive here is important actually. Had it not been attractive, there would have been no bound state. So a particle of mass m is subjected to an attractive delta function potential Vx is equal to minus V naught delta x, and V naught is greater than 0. Since V naught is greater than 0, this is attractive. Now find the bound state energy. So first we have to check whether there is bound state at all, and then after we have been sure, then we can proceed to find the bound state energy. Okay, so how to do that? So we start by writing the time independent Schrodinger equation. So this is the time independent Schrodinger equation, potential, and this is the energy eigenvalue. Now we'll solve this. So we know that the property of the delta function, like integrate it over all space and we will get 1, but delta x is 0 when x is not equal to 0. So this is the property of the delta function. and at x is equal to 0 this is infinite, so that the integral over all space is 1. So a strange kind of function, so actually it's a distribution, but that's not important here. So we need to look for two separate regions, like the potential is v naught delta x, so that means the potential is discontinuous at x is equal to 0, but the potential is 0 both for x greater than 0 and x less than 0. So except at x is equal to 0 the potential is continuous everywhere, and the value is 0 everywhere other than x is equal to 0. So, and naturally the x is equal to 0 discontinuity divides our 1D space in two regions, like, so one is x greater than 0 and other is x less than 0, and then x greater than, and we solve for Schrodinger equation separately for both of these two regions.
Sir?
Yes?
Sir, for the bound state, we need energy should be less than V minus V at plus minus infinity, and then energy should be greater than V global minimum, right?
Yes?
So, sir, how will we check V global minimum in the delta potential function? Because it will be the delta potential function will be uh, one at certain domain and elsewhere it is 0. So how will we find global minimum for that function?
Yeah, delta has no global minimum actually.
So sir, how will we, because the condition for bound state is we have to require two conditions. First, energy should be less than at v of plus minus infinity, and energy should be greater than v global minimum.
Yes, so v at plus minus infinity means, so here v at plus minus infinity is 0, as you can say. So that means we have to have energy less than 0. That is one thing. And okay. Oh, sorry, global minima, right?
Yes sir, global minima.
Yes, so of course it is already, so global minima is at minus infinity.
Yes.
Yes, so there is no problem. So all we need is, so v at plus minus infinity is 0. That
Yes.
means our energy has to be less than 0.
Yes sir.
And global minima is minus infinity.
Minus infinity, yes sir,
Yes.
that's the problem.
So no problem. So, and energy has to be greater than the global minima. Otherwise,
Okay, so
yes.
can we consider infinity as a greater than energy? Because infinity is not a quantity.
I mean, anything you take will be greater than minus infinity. Like any finite piece you take.
Finite. Okay. Thank you,
So,
sir.
what you have to do? So, you only need to consider E less than 0 case.
E less than 0 case.
Yes. So, E less than 0 case satisfy this plus minus infinity problem that you have said,
Yes, sir.
and then it is also greater than this global minima.
Okay.
So, we will have to look at E less than 0. Okay. And alternate characterization of the bound state is this one also. So psi at x tends to plus minus infinity has also has to be 0 also. So otherwise, like for free particle it is oscillatory. So that is why it's not a bound state. So something like that. So for bound state, psi at x tends to plus minus infinity has to be 0 also. So now, as we are discussing, so we need to solve the Schrodinger equation in two regions separately, one for x greater than 0 and for x greater than 0 our potential is 0 in that region. So for x greater than 0 we only need to solve this equation. And for bound state, as we have said, so we need psi x tends to plus infinity is 0. So that is what we need. And so okay, so suppose you did not know about these all the two criteria that you have just said, like this global minima criteria and v at plus minus infinity criteria. For this particular problem you can find, I mean you can invent them independently also. Like this is the Schrodinger equation for x greater than 0, and for bound state you need psi x tends to infinity is equal to 0. So given this boundary condition you need to solve this equation, and to satisfy this boundary condition you will see that you will already need e less than 0, because in this equation if you have e greater than 0, so then you will have oscillatory solutions. So that will be sine and cos kind of solutions if e greater than 0, but that will not satisfy this bound state condition, like psi has to be going to be 0 at x tends to infinity. And e equal to 0 is also problematic because that will give us a linear in x solution, and that will not be a bound state. So the only possibility is e less than 0. So I have just uh, reiterated your point in a different language. So for this to have decaying solution at infinity, e has to be less than 0. And similarly, okay. And similarly for the region x less than 0 also. Here again the potential is 0, and you solve this Schrodinger equation with this boundary condition psi x tends to minus infinity is 0. So again for that to have this decaying solution at minus infinity you will need e less than 0. Had e been greater than 0 it would have been a oscillatory solution. So we have e less than 0 and we write the solutions like this. So for x greater than 0 the solution is this: psi x a e to the power minus kappa x, with kappa is equal to this one, 2m mod e divided by h cut square whole to the power half. So I have taken mod e because as we have just discussed e is less than 0. So this is one solution, this is the solution for x greater than 0, and you see since kappa is positive and if you put x tends to infinity here, that means psi x tends to plus infinity decays to 0. And similarly this is the solution for x less than 0 region. So again kappa is positive. Now if you put x tends to minus infinity here, that decays to 0 again. Okay, so that was the solution. And now what about this a? So I have written both of them to be a. So ideally I should have written one as a1, another as a2. How do I do that? Because of the property of the wave function that it has to be continuous everywhere. So now this is the continuity even at x equal to 0, where the potential itself is infinite, I mean discontinuous. The wave function should be continuous. So this is the continuity relation at x equal to 0, So psi x tends to 0 plus is equal to psi x tends to 0 minus due to the continuity of a function. So use this continuity relation and then you will see that a1 and a2 both should be equal to a. So that is why I have not written them as separate a1 and a2. So both of them is a because of the continuity of wave function. Okay, up to that is fine. Now there is another property of the delta function. So the main property of the delta function will be used now. So consider this. This was the full Schrodinger equation. Now we will have a look around the region. So at the region around x equal to 0. So we will be looking at this region. So x belong to minus epsilon to plus epsilon with epsilon tends to 0 plus. So let us take this Schrodinger equation and integrate it around this region. So what do we get from the first term? We get this one. This is nothing but the first fundamental theorem of calculus. So psi dash epsilon minus psi dash minus epsilon. So I have integrated it up to minus epsilon to plus epsilon. So the first term gives us this. Now the second term, due to the property of this delta function, gives us b naught psi naught because that is the property of the delta function. So if you integrate it from minus infinity to, if you integrate it from minus epsilon to plus epsilon, that means that region includes x equal to 0 where the delta function is infinite. So by the property of the delta function, that integral should be psi of 0. So that is the property of delta function. And then the right hand side, this is the integral minus epsilon to plus epsilon. And what do we see? So there is another property that the wave function should not diverge. So since the wave function should not diverge and our region of integration is infinitesimal, that means it should be 0 because epsilon tends to 0. So we are left with this. So this is the left hand side and right hand side is equal to 0. And now simply substitute these two solution, take the derivative of this and put x equal to epsilon. That is what I have done here and obtain this. So psi dash epsilon. So psi dash epsilon means, so taking the derivative psi dash x means minus kappa a e to the power minus kappa x, and in place of x substitute epsilon, so e to the power minus k epsilon, and epsilon tends to 0, that means e to the power minus k epsilon gives us 1. So that is why I have written in minus ka. So just do that also for x less than 0 region, and psi 0 is a, right, from the continuity. So psi 0, just substitute x equal to 0 in both of the cases and you will get a. So we get this relation, and from there, so since a should not be 0, otherwise the whole wave function is 0. So since a not equal to 0, we obtain this and then substitute the value of kappa, this one, and we get this one. So this is the bound state energy of, in the delta function potential, and there is only one bound state because we can get only one solution to the Schrodinger equation that satisfy the bound state conditions. So that is that. Okay, so is there any question? Okay, so someone is asking about recording. Okay, the recordings will be available in the sorry, it will be uploaded in the YouTube. So, and you will be shared a link. So don't worry about that. So if no question about this delta function, then there is this problem of double delta function. So this problem is little bit more involved, but I want to go through it quickly because I have discussed the details in the previous problem, and but here are subtleties also. So let us see. So a particle is moving in the 1D and is confined by a double delta function potential. So the double delta function potential is this one, and this is attractive, so G greater than 0. So two delta functions situated at x equal to a and x equal to minus a. So attractive potential, had it not been attractive, there would have been no bound state again. So now, okay. Okay, there would have been no bound state. So now we have to find the bound state energy levels. So actually, after doing this problem, I realized that the bound state energy levels cannot be obtained in closed form, but up to some equation, and you need to solve those equations numerically. So let's see, the technique of the solution then. So you see, two delta function situated at x equal to a and x equal to minus a, and naturally our 1D space is divided into three parts. Okay, so one is the left hand side of the delta functions, that means x less than minus a. Another one is between the delta functions, and the third one is right of the delta functions, x greater than a. And of course, by the property of the delta function, the potential is 0 in all of these three regions, but at the boundary of the regions, the potential is infinitely discontinuous. So again, the standard algorithm is to write and solve the Schrodinger equation in each region, and then after solving in each region, so what to do? We need to do we need to use the continuity equation of the wave functions, and then there was a discontinuity in derivatives of the potentials that we discontinuity in derivatives of the wave functions due to the discontinuity in potential that we have seen in the previous problem. So we need to use those relations as well, and then you have to solve for the energy. So that is the algorithm. So we have divided the space And now we have to write the Schrodinger equation in each of these regions. So consider the first region, x less than minus a. So of course, again using the standard argument that we have discussed earlier, so the bound state can take e less than 0 values due to this global minima condition and this asymptotics of potential condition. So we have to have e less than 0. So again, please compare with the previous problem. So kappa square is defined similarly to a mod e divided by h cut square, and for bound state solution we need the wave function to decay at infinities. So that is why we have only considered e to the power kappa x, because in this region x to the power x less than minus a, because the the boundary, the left boundary of this region is x tends to minus infinity, and we need our wave function of this region to decay at x tends to minus infinity. So that is why this e to the power plus kappa x. Put x tends to minus infinity here and you will see the wave function decaying to 0 at infinity. So we cannot take the linear combination with e to the power minus kappa x here, because you see e to the power minus kappa x in this region goes to infinity as x tends to minus infinity. So that is excluded by finiteness of the wave function. So fine in this region. Now in region 2, potential is 0. So we just need to solve the free Schrodinger equation, and now you see you get this linear combination as a solution. We have kept two, both of the terms in this linear combination, because you see, because this region is bounded by minus a and a, there is no fear of this potential of this wave function to diverge to infinity anywhere. So that is why we are allowed to keep both of the allowed solutions. And why we cannot, and since e was fixed to be less than 0 earlier, so that is why they are decaying, so their exponential solution, they are not oscillatory sine cos solutions. So this is this, and in the region 3 the bound state solutions are a plus e to the power minus kx. Okay, so this plus is at subscript, right? It is looking like this is a plus e to the power minus kappa x. So that is not the case. This is a subscript plus and e to the minus kappa x. So again we have to take care of this decaying solution. That is why e to the power kappa x is excluded. Okay, so we have obtained the solution in 3 regions. Now let us use the continuity of psi x. So continuity of psi x at the two boundaries. So one boundary is this one. This gives us this relation 1. So I will not be discussing the mathematics very much because it is quite messy algebra. You just need to do it yourself once. And then there is the continuity equation at the another boundary, that is minus a, and put the solutions and compare, and you will get this equation 2. Now as I have said, so we have already used the continuity of a function. Now we have to use the discontinuity in the derivative of the wave function, and that arises because of this delta function. Okay, so like we did in the previous problem, so please compare with this. So in this case In the previous case, this was this one, so this equal to 0, and now we will have this one. So around x equal to a, again take the Schrodinger equation with the delta function potential, because around, so if we consider a small interval around x equal to a, so that involves the support of the delta function, and if you integrate uh, in that region, so the infinity of the delta function will come into play, and that will give a finite non-zero contribution to the Schrodinger equation. So this is that. So I have integrated around x equal to a, and then again substituted things. So just substitute the solution in both of the spaces, both of the regions, and then after algebra, so I am getting 3, and similarly do the same thing around x equal to minus a, like considering the discontinuity of derivative of a function, do some algebra, and you will get this condition 4. So we have these 4 conditions. So we have these 4 relations between our undetermined coefficients a minus a plus and b minus b plus. Okay, and now further substituting 3 in 1, and okay, this is just algebra. So substitute this, follow the steps that I have written. You get a plus by a minus and equal to b plus by b minus. And also from 3 and 4 comparing, you get this one. So now you compare this and this, compare these two, and you will get this condition. So a plus by a minus equal to b plus by b minus is equal to plus minus 1. So you see there are two conditions, one is plus 1, another is minus 1. So these two conditions will correspond to two defined solutions. Will correspond to two defined solutions. So in the first case, when a plus is equal to a minus and then b plus equal to b minus, from 1, okay, from 1, okay, substitute, so eliminate one of a minus, so eliminate a minus and b minus using this condition, and you will get this condition. So if you solve this equation, you will get a solution, a positive solution for kappa, because we need a positive solution for kappa, and that will give you the energy eigenvalue because of this relation, because of okay, get a solution for kappa, and you can get the solution for energy eigenvalue using this relation. Okay, so from the plus condition, we get this equation, and it has only one real solution, real positive solution as is required. So that is that one solution, and this is the even solution, parity even. So this is one solution, and then with the negative solution we will get another condition. So this is another equation. Solve this, get 1 kappa, you will get 1 kappa, but sorry, you will get 2 kappas actually. One is kappa equal to 0 and another is kappa greater than 0. But kappa greater than 0 is not allowed, because that will correspond to E equal to 0. But E equal to 0 is not a bound state. So for bound state we needed E less than 0. So kappa equal to 0 has to be excluded. So but this equation have another positive kappa solution, and that will give us another bound state. So that will be the parity odd solution, and that's the answer. So we have two bound state for any g greater than 0, and it can be checked that g less than 0 has no bound state. Okay, so enough with delta function. So now let us consider the final problem of today's session. So that is the simple harmonic oscillator. So I am considering only one problem from simple harmonic oscillator. So let the initial wave function of a particle in the simple harmonic potential be this one. Okay, where A is a normalization constant, we need to find that psi naught is the ground state wave function and psi 2 is the second excited state wave function. So we are given this our wave function is the linear combination. So our wave function at t equal to 0 is the linear combination of ground state wave function and second excited state wave function. So given the wave function at t equal to 0, we need to find the wave function at an arbitrary time and expectation value of energy as a function of time. Okay. So
Sir,
yes.
sir, can we not do it? We have given psi of x of 0 as a into 3 psi 0 of x plus 4 psi 2 of x as a linear combination of some states. Yes. So can we not write as psi of x comma t as this psi of x comma 0 into phi of t, where phi of t is nothing but e raised to minus I e t by h bar, and then we can solve for after using this phi of t by multiplying phi of t into psi x of 0, it will give us psi of x of t, and then using that wave function for finding expectation value of energy.
Uh,
That
yes.
would be easy one, I
Yes,
think.
that is what I am doing. Yes, you see, this is the Schrodinger time evolution equation.
Yes, sir.
Yes. Yes, as you were
Yes.
saying. So this is the time dependent of the first component. So
Yes, sir.
of course energies will be defined. So the time evolution of two components will be defined as you have expected.
Okay.
Yes. So because energy is different.
Energy is different for two different states.
Yes, two different levels. Yes, so this has energy. So this is the ground state,
Yes.
and this is the second excited state. So they have different energy.
Okay, sir.
They have different energy, and these problems can actually be solved much more easily when we will use this Dirac bracket notation.
Dirac bracket. Yes, sir.
Yes, yes.
Okay.
Like treating this components separately. I mean, it looks a little ad hoc, but
Yes, sir. It is
Yes.
little bit of mathematics.
Yes, but okay, for today, I mean, you need to do it like that. So from next week onwards, we will be considering bracket notation.
Sir, and one more thing,
Yes.
in the problem set of in this week problem set,
Yes.
I think question number. Wait a second.
So, okay, there is one question about this energy expectation value, right?
Yes, sir. That
Yes, that is
sir,
wrong.
because
Wrong.
yes, sir. In option there, my answer came up to be 3/2 h bar omega. It was question that let psi 0 and psi 2 denote respectively the ground state function and second state energy eigen function. We have to find, sir, exactly same question but different normalization constant.
Yes, yes. So, okay, you are getting 3 by 2, I was getting 11 by 6.
Okay.
Okay,
So
so the thing is, you have to add 5 by 3 plus 1 by 6. Yes.
सर मैं बोल रहा था कि ये जो आपने अभी क्वेश्चन लिया ना,
हाँ.
सेम क्वेश्चन एक होमवर्क में भी था.
Yes,
तो
yes.
उसमें जो
I know that.
तो उसमें जो आंसर आ रहा है वो मेरा जो आंसर आ रहा है और जो
वो
ऑप्शन
ऑप्शन
प्रॉब्लम
में
सेट
नहीं है. हाँ, वो ऑप्शन में
हाँ
नहीं
नहीं
है.
है.
हाँ.
तो
तो
फिर उसका क्या करना है, कैसे
I
करेंगे?
don't know what to do. I mean, let's put it 5 by 3. I mean, when you were putting it in
5 by
option.
3 ना.
Okay, you do it 5 by 3. So
5 by 3.
I would have gone with that.
क्योंकि सर इसमें मैंने 2 बार ट्राई किया. एक
Yes,
तो
yes.
E0 और
Yes,
E2
that is
के लिए
wrong.
है.
I
तो
know.
या तो E2 के मैं टर्म्स में निकाल लूं एनर्जी या फिर E0 को E2 के टर्म में. तो मैंने दोनों निकाल के देखा. तो एक बार जब मैंने E0 के टर्म में निकाला तो मेरा आंसर आता है 3/2 h बार ओमेगा. लेकिन जब मैं E2 के रिस्पेक्ट में निकाल रहा हूं तो मेरा आ रहा है 15/8 h बार ओमेगा. इसीलिए
नहीं, ऐसा तो नहीं होना चाहिए. मतलब आपको क्या करना है, मतलब वहाँ पे 1/3 एंड 2/3 था. मतलब वहाँ पे देखिए, मतलब एनर्जी एक्सपेक्टेशन वैल्यू वैसे होगा. मतलब 1/3 होल, सॉरी, √1/3 होल स्क्वायर
प्लस
मल्टी.
√2/3 का होल स्क्वायर.
तो 1/3 शायद ग्राउंड स्टेट का था, है ना?
ग्राउंड स्टेट का. यस.
हाँ, तो
और
करना ऐसा है कि 1/3 मल्टीप्लाइड बाई ओमेगा एच कट बाई 2
हाँ
प्लस 2/3 मल्टीप्लाइड बाई 5/2 ओमेगा एच कट.
यस.
हाँ, तो ऐसा करोगे तो मतलब वही 5/3 प्लस 1/6 आएगा. मतलब 11/6.
11/6.
हाँ, तो ऐसे करना.
तो फिर आंसर 5/3 करके छोड़ दूं?
हाँ, वो मतलब ऑप्शन देना है तो दे दो. यहाँ पे भी सेम चीज है. यहाँ पे भी बस नॉर्मलाइजेशन अलग है. तो यहाँ पे क्या किया मैंने, 3/5 होल स्क्वायर और 4/5 होल स्क्वायर. हाँ, तो ऐसा आंसर
नहीं. वो मेरे को इतना समझ गया था, बस मैं वही कंफ्यूज हो रहा था कि मतलब कुछ प्रॉब्लम के आंसर जो मतलब आंसर आते हैं और जो प्रॉब्लम सेट में दिए रहते हैं उसमें ऑप्शन नहीं रहते.
हाँ, एक ये था और एक शायद कुछ प्रॉब्लम 6 वाला था जिसमें,
हाँ, प्रॉब्लम 6 वाला जिसमें ae⁻⁰h बार प्लस be⁻⁰ बार, उसमें भी मेरा ऑप्शन गलत आ रहा था.
वो शायद 2 मॉड ए मॉड भी दे रखा था, है ना?
यस सर, क्योंकि मॉड ए मॉड भी तो कैंसिल हो जाएगा क्योंकि ये ऑसिलेटरी सॉल्यूशन है ना a⁻² वाले, तो a² - b² के फॉर्म में बनेगा.
हाँ, वो भी गलत है. ये मतलब जो लगे तुम्हें, मतलब सबसे नजदीक वो दे देना. हाँ, तो वही है. तो ये प्रॉब्लम डिस्कस करना है और ये फिर समझ में आ गया.
यस सर.
मतलब
नहीं सर, ये समझ में आ गया, मतलब उसी टाइप का है ये.
नहीं, वो तो है. मतलब ये टाइम इवोल्यूशन वाला, मतलब फाइनल आंसर ये है, टाइम इवोल्यूशन.
टाइम इवोल्यूशन
मतलब दोनों कंपोनेंट का टाइम इवोल्यूशन अलग है.
अलग अलग, मतलब आपने अलग अलग दोनों के लिए सॉल्व किए.
मतलब सॉल्व करना हो क्योंकि दोनों का टाइम इवोल्यूशन अलग है. क्योंकि एक का टाइम इवोल्यूशन E0 के रिस्पेक्ट में हो रहा है और दूसरे
हाँ,
का हो रहा है E2 के
ई टू
रिस्पेक्ट में।
के E2 के रिस्पेक्ट में।
हाँ, तो श्रोडिंगर इक्वेशन यही बोलता है। तो अभी सॉल्यूशन वैसा है, तो ये है टाइम डिपेंडेंट सॉल्यूशन। एंड देन अभी ठीक है, वो कैसे भी तरह कर सकते हो,
हाँ, ये
एक्सपेक्टेशन
तो
वैल्यू।
एक्सपेक्टेशन वैल्यू है।
हाँ वो ठीक है, अभी ठीक है, अगले वीक से और भी इजी हो जाएगा।
और रीजन है, हाँ ठीक है।
हाँ चलो ठीक है, बस वही है। सो दैट वाज दैट फॉर द वीक। सो
Yes.
आई हैव दिस मच टू डिस्कस।
तो सर आप ऐसे सेशन और भी लेते हैं या सिर्फ संडे को होता है?
नहीं, सिर्फ संडे को।
सिर्फ संडे को ना?
हाँ।
पिछले वीक भी हुआ था क्या?
नहीं नहीं, इस वीक
पिछले
से
वीक भी
शुरू
नहीं,
है।
इस वीक से शुरू है ना, ठीक है सर।
ठीक है, ओके। सो इफ यू हैव एनी मोर क्वेश्चन प्लीज फील फ्री टू आस्क।
यस सर। No sir, I have no question anymore.
Okay, so about others, so I guess no one has any more question. Okay, so if no more questions, so I will then end this session. So thank you for joining.
Thank you sir.
Okay, and then let us meet next week. Okay, bye.